Ever look at one of those, jumbled strings of characters, maybe in a QR code when you're trying to pay for something and think, there's got to be more to this than meets the eye?
Yeah, like some kind of secret language hidden right there.
Exactly.
Okay.
Okay, let's dive straight into that kind of thinking, because that's precisely where we're headed today.
Right.
This isn't just skimming the surface. We're plunging into the intriguing world of how data can be, well, tucked away inside what look like ordinary Base45 encoded strings.
Absolutely. And we've got a fascinating couple of pieces to unpack for this.
Oh, yeah. What are we looking at?
First, there's a paper titled ncdc.pdf. It introduces this really pretty clever idea of a way to symbolically compress data.
Okay, symbolic compression.
And then we have another one, hide45, a method for optimal payload data hiding in Base45 encoded strings.pdf, which really drills down into how we can most effectively stash extra information within these strings.
Got it. So our goal today, and you're here, so you're already on board, is to understand how data can be subtly hidden within these Base45 strings in ways that aren't immediately obvious.
Wait, what's really going on here? Moments.
Exactly. We're talking about those moments. We'll be pulling out the key ideas from these sources and aiming for those aha moments, without getting totally lost in a maze of technical details.
That's right. We'll be focusing on how the very structure of Base45 itself creates these unexpected opportunities for concealment.
So Base45. Remind us quickly, what's the basic idea?
Sure. Base45, as you likely know, is basically a method to take the binary language of computers, those ones and zeros, and translate it into a set of 45 characters that can be easily printed or displayed.
Right, which makes it super useful for things like those QR codes you mentioned. You need something scannable, compact.
Precisely. It's designed for that kind of application.
Okay, so how does this seemingly straightforward translation process unlock the potential for hidden data?
Here's where it gets really interesting. When Base45 takes two 8-bit chunks of binary data, that's 16 bits in total, right?
Right, 2 bytes.
It usually turns them into 3 Base45 symbols. Now, those 3 symbols, they have the capacity to represent a staggering number of possibilities. It's 45 cubed.
45 times 45 times 45.
Ah.
What does that work out to?
It works out to 91,125 different possibilities. A lot.
Okay, 91,125. But how many do we actually need for the original data?
And here's the critical point. To represent our original 16 bits, we only need 2 to the power 16 possibilities.
Which is 65,536.
Exactly, 65,536. So if we do the subtraction, 91,125 minus 65,536.
That leaves quite a bit left over.
It leaves us with a notable 25,589 unused configurations.
25,000 unused slots.
Pretty much. And the core insight here from both papers really is that this seemingly straightforward encoding creates a kind of hidden digital attic within each Base45 string.
Okay, I like that analogy, like having 91,000-ish storage boxes, but you only need around 65,000 to hold everything you have.
Right. That leaves a significant number of empty boxes. Those are our unused configurations.
And as both of our sources point out, that empty space isn't necessarily wasted space. It has potential.
Definitely. The Indistepa.pdf paper really delves into this idea. It introduces what they call an encoding field operator.
An encoding field operator?
Yeah.
Sounds technical. What's it do?
Well, what's fascinating here is their concept of using a symbolic operator to actually manage these very unused configurations.
Okay, so what's the role of this operator then? How does it work?
It's essentially taking that 16-bit binary string and performing the standard Base45 encoding, like usual, but then it goes a step further.
Oh.
The paper distinguishes between the legal symbol mappings, W, they call them the ones actively used to represent the original data.
Right, the standard.
And these excess configurations, D, which are the unused ones we just talked about, the leftovers.
Okay, so legal W and excess D.
And here's a clever twist. They identify a subset of these legal mappings, they call it E, that are eligible for what they call payload embedding.
Payload embedding. So hiding extra stuff.
Exactly. So these E mappings aren't just representing the primary data. They're also acting as signposts, basically, pointing towards those unused configurations in D.
Ah, so they do double duty. They carry the original meaning, point to a secret spot.
Precisely. This allows us to subtly weave in extra information, the payload.
Okay, how do they describe that? Is it like a switch?
They describe this as a transformation. You start with a base encoding, S0, and then there's this transformation that creates what they term a payload shadow, SE, within those unused configurations.
A payload shadow.
Yeah.
Interesting term. So back to the storage boxes. It's like some of your regular containers have, I don't know, secret compartments that open up to a whole other hidden storage area.
That's a pretty good way to think about it, yeah.
Okay.
And ends2c.pdf gets really intriguing when it starts exploring potential applications for this.
Like what could you use this for?
Well, they talk about steganography, first off, which
Yeah.
is essentially the art of concealing messages in plain sight, hiding things out in the open.
Right? Like hidden ink, but digital.
Kind of. They also bring up something called entangled symbol embedding and even recursive memory logic compression, hinting at some quite sophisticated possibilities down the line.
Wow. Okay, so that's the ink deck idea, using some standard codes to point to hidden payload space.
That's the core concept, yes.
Now, the second paper, Hide45, you said it focuses on optimizing this.
Exactly. Hide45 really grabs this idea of leveraging those unused configurations and runs with it. It focuses specifically on how to do it in the most efficient manner possible.
So not just using the space, but using it smartly.
Precisely. It's all about maximizing this hidden data capacity. Hide45 directly builds on the idea of utilizing that space, indeed the unused configurations, but it introduces a specific algorithm to strategically place hidden data there.
Okay, what's the strategy?
The core idea of Hide45 is pretty interesting. It's assigning bit configurations, meaning the ability to hide bits to the most frequent pairs of octets in the original data.
Most frequent ones. Okay, why does frequency matter so much here?
Well, think about it this way. If certain patterns of ones and zeros appear way more often in your data, say in a specific type of image file or something, then if we can embed more extra bits within the Base45 representations of those frequent patterns, we get a greater overall capacity for hidden data across the whole file.
Ah, I see. So you get more bang for your buck by targeting the common stuff.
You got it. The key takeaway is that smart data hiding isn't just about having space, it's about understanding the neighborhood of your data, and building secret passages, if you like, in the busiest areas.
So instead of just a simple approach like, I don't know, saying every unused configuration can hold one extra bit.
Right, which they call the baseline approach.
Instead of that, Hide45 takes a more nuanced approach. It's saying, let's actually analyze the data we're encoding first, and then strategically decide where to put the extra bits for maximum impact.
Exactly. They compare their method directly to that basic approach where you just use one unused configuration to store one bit of extra info.
And how much better does Hide45 do?
Significantly better. They report improvements of up to 53% in payload capacity over that baseline.
Wow, 53%. That's huge.
It is, yeah. And it's all down to employing this more intelligent assignment strategy based on frequency.
That's a substantial increase.
Yeah.
So how do they actually figure out this smarter assignment? It sounds like a complex puzzle to solve.
It is. It really boils down to an optimization problem, a mathematical challenge.
Okay.
The challenge is figuring out how to assign a varying number of payload bits to different binary sequences.
Right, not just one bit everywhere.
In a way that maximizes the average payload you can hide, but crucially, without exceeding the total number of unused Base45 sequences we actually have available. Remember those 25,589?
Right, you can't use more space than you have.
Yeah.
That makes sense. And they even have a formula for this average payload, don't they? Something like P equals.
Correct. It's P ogles ni phi. Sum over I of n sub I times f sub I.
Okay, break that down. What's N and F?
So, ni represents the number of payload bits assigned to a specific binary sequence I, and phi is the frequency how often that sequence I actually appears in the data you're encoding.
Got it. So multiply the bits assigned by how often it shows up, add them all up.
And the objective is to make that average payload P as high as possible.
And the constraint, as we touched on, is that total number of Base45 configurations we use for both the original data and our hidden payload. It just can't exceed that total possible number, the 91,125.
Exactly. We can't try to cram more into the attic than it can physically hold.
So how does assigning more bits use up more configurations?
Good question. If a particular binary sequence is assigned 9 bits of payload, say 3 bits, it effectively utilizes 2 to the power of 9 Base45 configurations. So for 3 bits, that's 2 cubed or 8 configurations.
8. Why 8?
Well, 1 configuration is needed for the original encoding itself, right? The standard one. And then you need 2 to the power of 9 minus 1, so 8 minus 1, which is 7 additional configurations from that unused pool, D, to represent all the different possibilities for those 3 header bits, 0, 0, 0, 0, 0, 1, 0, 10, and so on, up to 111.
Okay, so 1 standard plus 7 shadow configurations for the payload. Makes sense.
And the sum of all these used configurations across all possible binary sequences must stay within that 91,125 limit.
So in simpler terms, then, they're basically trying to give more secret compartments, more of those NI bits,
Yeah.
to the containers, the binary sequences that are used most often, the ones with hi-fi, because that's where they'll achieve the biggest overall increase in hidden storage capacity.
That's a great analogy. That's exactly the core idea of the optimization.
So how do they find this optimal assignment? Do they just try everything?
No, that would be computationally huge. The HIDE45 paper mentions using a linear program and a specific tool, a solver called CPLEX.
Linear program, a CPLEX.
Right.
What does that mean practically?
Think of a linear program as like a very precise mathematical recipe. It has lots of ingredients, the frequencies, the number of bits, and strict rules, the configuration limit.
Okay.
And CPLEX is like a super efficient master chef who can take that recipe and find the absolute best way to mix those ingredients according to the rules to get the, well, tastiest result, which in this case is the highest possible average payload P.
So it's a mathematical technique to find the best possible solution automatically.
Exactly. It uses these established optimization techniques to find the optimal assignment of NI bits to each sequence I, given the input data's frequency distribution phi.
Okay, that makes sense. Now, once you've used, say, CPLEX to figure out this optimal method for hiding data, how does the actual process of encoding and decoding work with HIDE45? It seems like you'd need some kind of, I don't know, key or guide.
You absolutely do. They describe something called an EncDec table. This table essentially holds the map.
The map between what?
Between the original binary strings and their corresponding base45 sequences. But, crucially, it also records how many payload bits, K, they often call it, if any, can be embedded within each specific mapping.
So this table is like the instruction manual. It contains entries for the standard base45 translations and also instructions on how to utilize those unused sequences for the hidden data.
Exactly right. They outline two main types of entries in this table.
Okay.
Type 1 entries are simple. They're for those base45 sequences that don't carry any payload, just standard encoding.
Straightforward.
Type 2 entries are for the binary strings that can carry, say, K bits of payload. For these, the table does two things. It gives you the original base45 sequence, and it links that sequence to a list of 2 to the power of K-1 specific unused sequences from that D pool we talked about.
So it points to the exact shadow sequences to use for the payload bits.
Precisely. It lays it all out.
Okay, walk us through the encoding process then, maybe at a high level. How would that work using this table?
Sure. So when you're encoding your data, first, you take a 16-bit chunk, convert it to base45 just like you normally would. Standard process.
Okay.
Then you look up the resulting base45 string, or maybe the input binary string, in your pre-calculated encodec table.
Right. Check the instructions.
If it's a type 2 entry, meaning it allows payload embedding, say K bits, you then read the next K bits from your separate payload data stream.
The secret message bits.
Exactly. And you use the value of those K bits, treating them as a number and index, to select one of those associated unused base45 sequences from the list in the table. And that's the sequence you actually output.
Instead of the original standard one.
Right. But if the table lookup shows it's a type 1 entry, no payload allowed for this one, then you simply output the standard base45 sequence you calculated initially.
Okay, that seems logical. And decoding would presumably be the reverse of that.
Precisely. When you receive a stream of base45 symbols and you want to decode it, you take a 3-symbol chunk. First, you try to convert it back to binary using the standard base45 rules. Then you check, is this base45 sequence one of the known unused ones that's listed in our encodec table as a payload carrier?
Okay.
If it is an unused one, you consult the table again. The table tells you, this sequence corresponds to index X for payload bits, so you recover those K payload bits. And crucially, the table also points you back to the original standard base45 sequence it replaced.
So you get both the hidden bits and the original data back.
Exactly. Then you convert that original base45 sequence back to the original 16 bits of binary data.
And if the sequence you received wasn't one of the special unused ones?
Then it's simple. If it's just a standard base45 sequence, a type 1 situation, you just convert it directly back to the original 16 bits of binary data using the standard rules. No payload involved there.
Got it. So this encodec table really is the Rosetta Stone, isn't it? It's essential for both concealing and then later retrieving the extra information.
Absolutely. It holds all the mapping information determined by that optimization process.
Now, what kind of real-world impact does this actually have? You mentioned the HIDE45 paper details some experiments. What did they find with different file formats?
Yeah, they did. They conducted tests across a pretty good range of common file types. Things like JPEG images, TIFF files, PNGs, ZIP archives, BZ2, GZ2, even PDFs and MP3 audio files.
Okay, quite a variety.
And what's really interesting here is the variability in the payload gains they achieved. It wasn't the same across all those different formats.
Right. We saw earlier that PDF files, for example, showed a really significant increase up to that 53% compared to the basic 1-bit method.
That's right. PDFs were the highest gain they reported.
But other formats showed smaller improvements. What explains that difference? Why are PDFs so good for this?
Well, it all boils down to what we discussed earlier, the frequency distribution of the underlying binary data within those file types.
5 values.
Exactly. If a particular file format, like PDF apparently, tends to have certain 16-bit binary patterns that occur much, much more frequently than others, then the Base45 optimization has a greater opportunity. It can assign more payload bits, a higher nigh, to those very frequent patterns, and that leads to a much larger overall increase in hidden capacity for the whole file.
That's a real aha moment right there. It's not just about the encoding method itself, the Base45 structure, but it's also deeply connected to the inherent statistical characteristics of the data being encoded.
Absolutely. It's the interplay between the encoding's potential and the data's actual patterns.
So a PDF file, structurally, must have some particularly common binary sequences that this method can really leverage.
That's the logical conclusion from their results, yes.
And this enhanced data hiding capability.
Mm.
What could it actually be used for? What are the suggested applications?
Well, the paper suggests some pretty practical possibilities. Things like embedding more robust digital signatures or maybe watermarks for copyright protection, embedding them directly within the data stream itself.
So it becomes part of the file, harder to remove.
Potentially, yes. Or even adding extra security-related information, metadata perhaps, hidden within the encoded data.
Interesting. Now, looking ahead, the paper also touches on some limitations and potential avenues for future research. What are some of the trade-offs involved with this Base45 approach?
Yeah, they do mention a key trade-off. Their current optimization relies on average frequency distributions. These are calculated across many files of the same type, like averaging across lots of JPEGs or lots of PDFs.
Okay, so using a general profile for, say, PDFs.
Right. And while their results show this works pretty well, with low variation usually, if you happen to encounter one specific file that has a very unusual, very atypical frequency distribution, then the pre-calculated average-based optimization might not be quite as effective for that particular file. The index table might not be perfectly tuned.
So the ideal secret compartment layout, based on the average, might not be perfectly suited to every single individual container or file.
Exactly. That's a good way to put it. They actually suggest that optimizing the index table specifically for the frequency distribution of a single file could potentially lead to even better results for that file.
A custom table for each file.
Right. But there's the trade-off.
What's the catch?
You would then need to transmit that custom encoding table along with the file itself, because the decoder needs that specific map.
Okay, so that adds overhead. The table itself takes up space.
Exactly. So it introduces a trade-off in terms of overall file size or transmission size. Is the extra hidden data capacity you gain worth the increased size from, including the custom table?
Right. That's a question for ongoing research, maybe specific use cases.
Precisely. It depends on the application. They also mention ongoing research into potentially different optimization methods beyond linear programming.
It's a balancing act, isn't it? Always trade-offs.
Pretty much always, yeah.
But the fundamental takeaway here, it seems, is that by truly understanding the underlying structure of something like Base45 encoding and combining that with knowledge about the recurring patterns within our data, we can discover these ingenious ways to utilize what appears to be just empty, unused space, use it to our benefit, and embed additional hidden information.
Absolutely. And it really highlights how even seemingly simple, established encoding schemes can contain surprising levels of complexity and, potential for innovation when you look closely.
So just to quickly recap our deep dive then, we've explored how Base45 encoding, while intended to represent binary data in a printable format, inherently creates this pool of unused configurations, that digital attic.
Right, the 25,000 or so extra possibilities.
We then examined how the encoding concept provides a framework, and the Base45 algorithm specifically exploits these unused spaces to hide additional data, the payload.
With Hide 45 really focusing on optimizing this process, making it smarter by basing it on the frequency of data patterns to achieve those significant improvements in payload capacity, especially for certain file types.
And hopefully you listening now have a clearer understanding of how this seemingly invisible layer of data can exist within these encoded strings. And maybe more importantly, why understanding the statistical properties of the data itself is so crucial for maximizing this potential. It's not just about the code, it's about the data too.
Well said. That interplay is key.
Which brings us to our final thought for you today. Considering the sheer volume of digital data we exchange, constantly, every single day, what are the broader implications, both the exciting opportunities and maybe the potential challenges, if these kinds of hidden data capabilities become more widespread and maybe even more sophisticated in the future?
Yeah, that's definitely something to think about. What does it mean if data isn't always just what it appears to be on the surface?
Exactly. Food for thought. Okay, thanks for joining us for this deep dive.